Hello wonderful people, welcome to Cosmology Talks. Today we have Melissa Diamond, who is a postdoc at Queen's University in Canada, and we're also joined by Chris Cappiello, who is a co-author on the paper Melissa's talking about, and he's also a postdoc at Queen's University in Canada. They're talking about light-dark matter and its possible interactions with light and with charged particles. Of course, we know it can't interact strongly with such particles, but it can interact weakly, and many experiments are looking for this. And in particular, they've noticed some previously less explored interaction pathways that could essentially mean that a bunch of already existing well-motivated models of light-dark matter might interact more strongly with light and charged particles than previously thought. I'll let them get into the details. This is interesting because it means that constraints are potentially stronger on these models than we thought, and the hopes of detecting evidence for them in future direct detection experiments is larger. One thing I'm quite keen to hear about is whether the parameter regions that are being opened up match well-motivated parameter regions for these well-motivated models. So welcome, Melissa and Chris. Do you want to start by telling us briefly about your paper?
The basic story with what we did here is that using these loops, which I think we'll talk about in a little bit more detail soon, we found a way to calculate an effective dark matter electron cross-section if you start with a dark matter proton cross-section. And what this means is that we can then look at dark matter experiments that rely on electron interactions to get constraints on dark matter proton cross-section, so we can sort of either get a new way to explore parameter space there, or we can block off parts of parameter space that we weren't able to really access using direct detection, at least the traditional sort of nuclear recoil way.
If people are thinking of this talk or your paper 6 months from now and there's only two things that they can remember, what would you want those two things to be?
So I think one big thing I want people to take away from it is the idea that when we assume dark matter talks to the standard model or interacts with it in some way, because the standard model is something where all the particles interact with each other already, once we get dark matter interacting with any piece of the standard model, it can interact with the whole thing. The other interactions are suppressed, but they're still present. And this means that dark matter interactions with one particle can cause dark matter interactions with other particles, and that can give us sort of new ways to look for dark matter. And we did sort of one specific scenario here, but I think it's really more broadly applicable beyond just the calculations that we did and what we demonstrated.
All right, yeah, so why did you do this? What questions were unsolved that you wanted to solve, and why were they unsolved? Why did you want to solve them? And what makes this relevant today? Why did you release this paper in 2023 and not 2021 or 2025?
Well, when we started, and this might sound funny, we thought this would be a simple calculation, and we were sort of wondering why nobody had done it before, which I'm discovering is dangerous. If nobody's done it, a lot of the time that's because it's hard or you can't do it. In this case, it turned out because it was hard. So people have done similar calculations in the past with electron loops. So these are some of the different interactions that we were dealing with, where we've got Feynman diagrams showing dark matter scattering off of the P's are standing for protons. And we started with a tree-level interaction, and then we made proton loops, and we had to add in a couple of other loops. But people had done the reverse, where they had dark matter which could scatter electrons at sort of a basic tree level, and then put electrons into loops and discovered a way to get scattering off of nuclei. And that was very useful. That was done a few years ago. So part of the reason people hadn't done it is because once you work with nuclei, you have to involve like quantum chromodynamics, and that is kind of messy to work with. And then additionally, I don't know that the electron recoil detectors were that great or that functional in 2014 when those calculations were done. And now we've got Sensei, which has already taken a bunch of data, and we've got a couple of other electron recoil detectors, which are like DAMIC M, which is up and running, but hasn't finished taking data yet, which look really promising for allowing us to explore parameter space that other detectors can't. And I just don't know that these existed at the time, because the loops give you a really big suppression in the interaction cross-section. So you need a situation where you have some kind of detection method which is much, much better than what you could normally do with a tree-level detection, because you're dealing with a very suppressed comparative cross-section. So I guess it's kind of all those things together.
So yeah, what is chi? Chi, I guess, is the dark matter, and then what is Z prime? What is going on in these figures?
So here what we're looking at is chi is the dark matter, and Z prime is a vector mediator. So this is something which we're assuming the dark matter doesn't interact directly with anything in the standard model, but that the Z prime is what talks to both the dark matter and the standard model. Now, this is sort of a common way to get dark matter to interact with the standard model, because this gives you sort of a weak interaction. So the P's are for protons. So in the first, the one labeled A, what you're looking at is just dark matter coming in, and it's interacting with the proton by exchanging this Z prime, and then they both go off on their way. So this is sort of what you would expect for a normal dark matter hits a nucleus and they scatter and exchange momentum. And that's what a detector would see. So these other loops here, like B, C, and D, these are all using the fact that dark matter interacts with protons to get an effective electron interaction. So in the plot B, we've just made the protons into a loop, and the gamma is for a photon, so they're emitting a gamma ray, you could imagine. And then we're scattering off of an electron now instead of protons. And then the last two, the pi's are for pions, which are a light meson, and they're sort of the main player when we're dealing with low energy quantum chromodynamics, or QCD.
Z prime is a way to get an interaction with the standard model, but why should there be one? Is there observational evidence that there could be, or is that got something to do with the generation of the dark matter in the first place? It has to be made. Why would there be this interaction?
Yeah, no, that's a great question. Dark matter doesn't need to have any interaction with the standard model necessarily. So there are mechanisms to produce dark matter without involving any interaction with the standard model at all. I guess I would say that the problem is, since we don't know what dark matter is, as a community we're sort of taking a multi-pronged approach where we're considering all the different possibilities and exploring them. So it's easier to make dark matter if it interacts with the standard model, and right now we've put a lot of effort, we've set up a lot to try to explore that possibility, and so this is just sort of a helpful tool, I would say, in exploring that.
I guess there's also the fact that the dark matter density and ordinary matter density are so similar that if they got produced by entirely independent mechanisms, it's quite a freakish coincidence, but if they do interact, it's not so surprising that they come out with roughly similar densities at the very end.
Yeah, certainly. Normally the way that you produce dark matter, or one way that I've seen to produce dark matter without interacting with the standard model, involves like producing a bunch of black holes and then letting those decay, and that might produce everything. And there I think it's not so difficult to have similar amounts of each, but it is also not so difficult, or it is maybe more straightforward to have both particles kind of coming from a similar origin, or where they sort of interact weakly and they get produced together early on. This other sort of motivational slide showing you sort of dark matter, the parameter space as we've explored it so far. On the bottom, we've got the dark matter mass in terms of MeV, or GeV, and then on the left side, we've got their interaction cross-section with atomic nuclei. So in the dark gray and the light gray are different constraints on dark matter interactions with the standard model, just based on what we've been able to observe so far. The dark gray is based on nuclear recoil detectors. And these basically rely on dark matter coming in, smashing into a nucleus and causing it to bounce back or move in some way, and then us trying to detect that happening. As we get to lighter and lighter dark matter, though, it has less and less momentum, and so it starts to not be able to hit the nuclei hard enough to get any sort of observable signal. And that makes this sort of window that I've circled here difficult to reach and explore. So the other part of the motivation is that if we were instead relying on electron recoil detectors, well, that's a much lighter target, and so you can much more easily explore dark matter in this mass range, smashing into electrons, than you can that dark matter hitting nuclei. So part of the motivation is that we've got this window where, if only we could somehow use electron recoil detectors, we would be able to explore this area that we can't really with at least the detectors that are, currently running.
Okay, so yeah, you mentioned Sensei and Damic M earlier.
Yeah, I can talk briefly about them. Sensei and Damic are both solid-state detectors in contrast to, for example, the strongest limits on dark matter and nucleus scattering come typically from liquid xenon, liquid argon, and for spin-dependent scattering, things like pico, which is a fluorine bubble chamber. For dark matter with masses of sort of a GeV and above, scattering with nuclei, a lot of the strongest limits come from these liquid xenon or liquid argon detectors. If you get down to lower masses, it's very difficult to use these detectors just because of sort of a combination of kinematics and energy threshold and how the readout is done. So the way that you look for a signal in something like a xenon detector is dark matter hits the nucleus and it goes recoiling through the detector, and then every atom that it interacts with has a chance to get excited or ionized, and you look for sort of the bulk signal from all of that. With a detector like Sensei, you're able to look for a single electron getting kicked off, and that's what lets you get really good limits down at very low mass.
So what is Sensei's material?
Yeah, both Sensei and DAMIC-M use silicon-based CCDs, in contrast with a detector like Xenon, which uses, of course, xenon, or detectors like Deep and Dark Side, which use argon.
What does CCD stand for? That's like it's a camera, right?
It's a charged coupled device, yeah. It's essentially a very sensitive ionization detector.
Oh, I see. Okay. And so do they have like a huge array of these or just one clump of silicon or?
Yeah, the Sensei detector that we use data from is a single 2-gram CCD. So it's very small compared to something like LZ or Xenon N-ton. And DAMIC-M is going to be much larger, and there are plans to make a version of Sensei that is larger by 1 to 2 orders of magnitude.
So these things are still put deep under the ground though, so that background noise is not infiltrating.
Yes. Sensei that we look at here is in the Minos cavern at Fermilab. It's about 100 meters underground, so it's not as deep as some things like Lux or Xenon N-ton that are 1 kilometer or 2 underground. So it's a little bit shallower, and actually that lets you get up to slightly larger cross sections, although it does affect the background rate.
Before I let you go on with what else you want to say, this blue cosmology line is fascinating, especially for a channel called Cosmology Talks. What is the physics behind that blue line constraint?
Okay, so that is an older version of the plot, but yes, that's from Lyman alpha constraints, I believe.
Yeah, it's a Lyman alpha constraint, which is a way of measuring structure formation. So the idea is basically that if dark matter interacted too strongly with ordinary matter with protons in the early universe, the transfer of energy between those two populations would affect sort of the growth of density perturbations in the early universe, and that would get, what's the word I'm looking for? You can propagate that forward into present-day observables, and so you can set a limit on how strong this interaction is.
Awesome. Let's get into the details then. What is the new sensitivity with taking into account these loops, and what does it open up for Sensei and DAMIC and other new probes, and maybe a few details on how to actually do the calculation?
Sure, okay. I guess I can start with the plot so you can see what you get out of this, and then, because I can pull those up more quickly. So these are, we've produced a couple of plots, but the first one, that set that I'm showing here, we've got the original constraints that I had sort of shown you previously, but now we're putting what we've contributed on top of it. So the red area, that is constraints that we get from Sensei. So really all we've done is we've taken the limits Sensei produced on dark matter electron interactions and recast them into limits on dark matter nuclear interactions. And then the dotted regions, or the outlined regions, this is the sensitivity that we expect to get for DAMIC-M, which is already running, it's already taking data right now. And then Oscura, which is an upcoming electron recoil experiment. So this is for a heavy mediator. So that would be assuming that Z is heavier than the amount of momentum that's being exchanged between the dark matter and, whatever it happens to be hitting. And we've also considered 2 different cases here. And I guess I'll get into this maybe a bit when I do the calculation. But we have to sort of start our calculation at quark level and then build up what is the interaction with nuclei, and then what does that interaction give us in terms of an electron interaction. And so we have to make some kind of assumption about how the dark matter interacts with quarks when we do these calculations. So we're showing two different cases here just to show you how much changing your dark matter quark interaction affects the result. So on the one side, what we're assuming is alpha up and alpha down. These are just the couplings to the U up quark and D down quark. S is for the strange quark.
So you said your red ones come from the sensei cross-section with electrons that has been constrained. And what your data here is saying, if there was a nucleon cross-section, through these loops there would be an electron cross-section. Therefore, based on these constraints that Sensei have quoted on electron cross-sections, there is also a constraint on nucleon cross-sections. If all of that is true, what is the grey Sensei thing that pre-existed? Is it some direct constraint on nucleons somehow?
Yeah, so those are constraints that come from something called the Migdal effect. To my understanding, that is when you hit, your particle hits a nucleus and ionizes it by hitting the nucleus hard enough to separate a nucleus from the electron. And then since it's sensitive to electrons, this detector will see sort of your newly freed electron in that way. So this is dark matter hits the nucleus instead of dark matter hits the electron.
Your red thing is just weaker than the grey one, right? Like, so the Migdal effect is more significant than your one. You've shown that, of course, with Damic M and Oscura that your thing will be much, much better than Sensei, but what would the Damic M and Oscura Migdal effect constraints be? Have you found something that is better than that, or is it still subdominant?
Yeah, there is a paper out there that shows projections for what a Migdal effect search with Damic M and Oscura would look like. Unfortunately, those projections, the only ones that I've been able to find in the literature, only go down to a mass of about 20 MeV, so they don't cover a good chunk of the parameter space that we're showing. If you were to extrapolate them down to arbitrarily low mass, you can sort of squint at it and say that there would be some parameter space where we would beat them by a bit, but it's hard to say without knowing how those projections were done and how and whether it's reasonable to extrapolate them.
And if you had your Damic M detector, are there things about how the electrons are being scattered that would allow you to tell the difference between a direct interaction with the electron, or direct via loops, or an interaction with the nucleon that then spat out the electron? Is there a way to tell, based on the electron that comes out, how it got spat out?
I think, in general, an individual electron, it would be very difficult to see, it would be very difficult to tell the difference. You know, suppose we were living in the future and we had detected dark matter and there were many, many events going on. The event spectrum or the recoil spectrum of the two processes might look significantly different. For example, the energy spectrum of signals that you get from the Migdal effect versus signals that you get from just ordinary nuclear scattering are very different. And so I would not expect that those spectra would be quite the same, but it's something that you would need a lot of statistics to differentiate.
Yeah, I suppose if and when one of these detectors actually detects dark matter, the next wave of detectors will have very precise mass and cross-section sensitivities in order to work out all of this stuff in much more detail. Melissa, you were about to go into the details of...
The way that we go through this is in order to calculate a tree-level proton cross-section or to calculate a loop-level calculation, we have to start off with quarks. Because even when we're thinking about dark matter scattering off of nucleons, what we're really talking about is an underlying theory where the dark matter is scattering off of the quarks or interacting with them in some way. Now, once we introduce quarks, we have to introduce QCD, which is quantum chromodynamics, and that can be a bit of a pain. And the reason it's a pain is because at very high energies, quarks are free. We can think about individual quarks. As we go to lower and lower energies, their interactions become stronger, and the calculations to deal with them become increasingly complicated. So one way to deal with this is at the lowest energies, we can use something called chiral effective field theory, which says the quarks are so strongly interacting They don't behave anymore as quarks. They're now sort of trapped into these low energy states where they're either protons or neutrons, or, like, most importantly at these low energies are light mesons, which are, in this case, pions. So light mesons are just two quarks that are, confined and bound together. A pion is an up quark and an anti-down quark. And because these are light compared to protons and neutrons and the other mesons, these are really sort of the dominant force carrier for QCD at these low energies. So in order to talk about what's going on, even with like having protons or neutrons sort of acting in these loops, we actually have to also think about these pions and light mesons because they end up being kind of the dominant player once we open ourselves up to thinking about dark matter talking to quarks. The way that we have to do all of this is we'd start with this interaction, which just describes how does dark matter talk to the quarks. So in this case, we're summing over interactions with all the quarks. Each quark, we've got a unique coupling to it, which I'm calling alpha here. The Z prime is appearing, and that's just our dark matter mediator. I'm just saying this talks to quarks, and the gamma here is indicating that it's a vector coupling, so that's the type of interaction between the quarks and the Z prime. And this is just the interaction term in the Lagrangian that's describing how all the particles are interacting and behaving. If we start with this, we can build up our effective proton interaction and our effective pion interaction, and then we can get kind of a consistent picture of how dark matter talks to all these different particles, and then basically what are the effective interactions and cross-sections we get from that.
And just a quick question to make sure I'm getting the story right again. Like a proton and a neutron have mass of around about 1 GeV. So the light dark matter, or just in general dark matter, has access to two forms of, I guess, energy. It's mass and it's kinetic energy. If you've got a dark matter particle that is a GeV or more, it is likely to have quite a large possibility to have kind of proton loops because it's got enough energy to kind of excite a proton in a loop. Whereas a light dark matter that's less than 1 GeV would have to be traveling very, very fast for that to be the relevant thing. And that's why the mesons are the relevant thing here, because their loops are kind of more able to be excited by a light dark matter. Is that the kind of right story, or am I completely way off here?
Yeah. So it does. All the loop terms are sort of a suppression term, and as you increase the energy of the interaction, that suppression is weakened. It's easier to access more states. Because the energies we're dealing with are sort of below the mass of both the pion and the proton, their masses are really important because their masses are sort of dictating how strong the suppression is. And because pions are lighter, their contribution is less suppressed than what protons are contributing. We're building up like effective interactions now, so we can start with just like what is a proton effective interaction, because we need this to build our tree level diagram and our loop level ones. So protons are fermions, quarks are fermions, and so they kind of behave in the same way, and that makes it a little bit easier to figure out what their interaction is. But so the interaction has the same form. It's also a vector coupling. And the sort of strength of that interaction is basically just dictated by what are the quarks that go into a proton. So a proton's made of 2 up quarks and 1 down quark. And so the strength of the coupling is just 2 times the strength of the coupling to the up quark plus the strength of the coupling to the down quark. We're just adding up all the pieces. And that's what this interaction looks like. And this is what we kind of like stick into our calculations when we do them.
I guess very naively, I'm surprised it's so linear and that there's not like all sorts of back reaction of quark on quark and this and that.
As we turn up the energy, you'll get more of that. Well, one, we're doing this as a bit of an approximate calculation, but then 2, we're at low energies, and so the extra contributions are smaller than sort of this main one.
And gluons aren't relevant at all here, that there's like lots of gluons floating around in a proton, and presumably they would interact with Z prime, or is Z prime not color related? It's something else.
So in this case, we're assuming, I'd say that Z prime's not, it'd be color neutral, or that's not figuring into how it's interacting with the quarks. You definitely can build models where you fold that in. We were sticking with, I guess, like a simpler one for this calculation at least.
That's the benefit of coming first.
Yeah, we get to do the easiest version. We let other people do the harder version. I guess in a way you could think about the gluons are here and participating because they're forcing us to think about protons and not quarks. Like, it's those strong quark interactions with themselves that have moved us from being able to talk about quarks at all to needing to talk about confined quark structures. So pions, it's a little bit trickier to figure out what their effective interaction is because they're scalars, they're not fermions, and so they have a different interaction. They have sort of this derivative scalar coupling to the Z. And then, incidentally, sort of conveniently, the effective coupling that we can get for these objects is also ultimately just counting up the interactions with the quarks, where it's, one up quark minus a down quark, and that's how this ended up working out. But this is sort of our effective interaction. Both of these come from the same underlying theory, so whatever theory you happen to pick, whatever quark interactions you want to pick, this is how they relate to each other. And then if we use these and then do our calculations, we can have, for a given dark matter theory where dark matter interacts with protons, here's its matching loop calculations that would go along with that specific starting theory.
Why is the dark matter a fermion, or is it just, you have to start somewhere and do the calculation? And why is the Z boson a vector?
Part of it was just we had to start somewhere, and this was a sort of straightforward model to work with. These are common models, these are sort of popular models, I'll say. The dark matter being a fermion is not hugely important to the calculation. We're going to end up getting a ratio between a dark matter electron cross-section and a dark matter proton cross-section, and the dark matter is a fermion piece of both of those cross-sections kind of divide out in the ratio. So it's not hugely important that the dark matter is a fermion. It is important that we're dealing with a vector. We're connecting to the standard model using a photon. So we've got our Z prime, a loop, and then a photon. And all of these loops would go to zero if I weren't working with a vector. We can only sort of get this kinetic mixing with a photon if the object on the other end of it is a vector the way a photon is a vector. Now, that's not to say we can't connect to the standard model through other mediators. So if the Z prime were a scalar, for example, that would be fine. We could still talk to the electrons, but we can't use a photon anymore. We'd have to use another scalar, like a Higgs, and that would just be more suppressed and sort of a weaker effective interaction. So we also picked this because this is kind of a best case scenario, at least naively, when you're doing the calculations.
Yeah, the other alternative, if you want to still have a photon in that scalar case, is you can have a diagram like these loops, but where two photons come off of the loop instead of one, and so then you'd be looking at a two-loop process, and it's a calculation that you can do, but there are basically additional factors of the fine structure constant of 1 over 137 that get thrown in, and so the cross-section becomes parametrically smaller by a couple orders of magnitude.
Okay. And I guess the same reason why we're at low energies and therefore quarks are confined, blah, 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 blah. It is a photon, not a W or Z boson. We're at low enough energies where electroweak is not relevant at all. It's just photons.
Oh, we could have done the electroweak calculation as well. It's just smaller than what the photon contribution would be, at least at these energies, because those are heavy mediators, their coupling to electrons is weaker. Taking all of that that I just described, we can sort of write out all these different Feynman diagrams and then use the couplings that I showed on the last slide to go through and calculate what all of them are relative to each other. And we have our one tree level one, and then we've got these three different loop level ones. We have to add all of them up. They're all contributing. And I guess to your question, theoretically, we could also fold in like a W or like a Z. Standard model Z could also be contributing to these, but it's smaller, so we're not going to worry too much about its contribution.
This D diagram is puzzling me. Is this saying that the photon and the Z prime have some direct interaction with each other via a pion?
Yeah, so once we introduce this scalar style interaction, we can't really, we don't get just the one interaction, we get both of them together. So the same thing happens in scalar QED, or scalar quantum electrodynamics, where electron interactions with the photon sort of necessarily have these the balloon type diagrams and then the normal sort of bubble ones.
Okay, like if I was just to look at that vertex, I've got a z prime, 2 pi's, and a gamma. I guess that's not included in your Lagrangian at the bottom.
Yeah, I've got my pion-photon interactions. Those already exist. And then when I introduce my Z prime pion interactions, there's sort of necessarily like a cross term that comes out of that. So we get the Z proton pi interaction appearing.
There actually is a parallel to this in the standard model in the electroweak theory. You have a 4-point vertex like that. If you have a photon, a regular standard model Z, and then a loop made of the W boson, that is a diagram that exists. In the standard model, it's a little different because the W is a vector, not a scalar, but it's a similar idea.
We put all of that together. I calculate the Feynman diagrams, and these are the different diagrams I'm calculating, sort of using those Lagrangian terms that I had described. And when I add them up, what we get is that the electron cross-section is effectively the proton cross-section times these adjustment terms. We've got the loop contributions, which I've separated off. So the top one is coming from the proton loop. This next second one, that's from the pion loop and the kaon loop. They're all sort of a very similar loop calculation, so all of these terms have more or less the same form. And then in sort of the main body of the result that we get, we've got the reduced mass of the electron and the dark matter over the reduced mass of the electron and the proton squared. That's just coming from the fact that we were scattering protons, now we're scattering electrons. That kind of changes the kinematics, and that affects the cross-section that we get. Because we've got a whole extra photon here as compared to this diagram. We've got two different interactions. We get an extra factor of E, that's where the E squared is coming from. And then the rest of this suppression is more or less from the fact that we're dealing with loops now.
And even though it's the meson interactions that are like the more relevant, more strong ones, you kind of just chosen to parameterize it as a multiple of the proton cross section because that's something that people are familiar with, that pre-existing constraints exist on, etc. It's not saying that it's somehow the important cross section. It's just saying this is the kind of reference amplitude cross section.
Yeah, I mean, this is the cross-section we have access to. This is the one people want to get constraints on. So this is the one we're sort of using to compare to like these electron scatterings. Just to show you the way that this effective cross-section varies depending on how we vary the model, what your favorite dark matter model is, and what you stick into our calculations. So here we're assuming that the Z is heavy, would mean it's heavier than the amount of momentum that's being exchanged between the dark matter and whatever we're knocking the dark matter into. On the left side, we're showing we've assumed that the coupling to the up quark and the down quark have the opposite sign, and I'm ignoring coupling to the strange quark. This is a case where we'd have contributions from both light mesons and from protons. The red region, this is ruled out by observations from Sensei already. So Sensei has much stricter constraints on the electron dark matter cross-section, and then we can just turn that into a constraint on the dark matter nucleon cross-section because we know how to relate the two cross-sections to each other now. On the right, this is if we set all the quark couplings to be equal to each other. So as you saw, the meson couplings would go as like alpha U minus alpha D, something like that. And so when we set the quark couplings equal, all those meson couplings go away. And so this is just a case, because it's a reasonable model to consider if a proton-only case as well. And it's weaker because the mesons kind of those are a somewhat dominant term in the calculation. And so we've outlined in dotted red, this is sort of what we expect the constraints or the observable region to be for upcoming detectors. Atomic M is already up and running. Oscura is not running yet. It's sort of a future detector. This is a heavy mediator case. We could also consider a light mediator, and we actually do a bit better with a light mediator. So the Z is now light compared to however much momentum we're exchanging. And in this case, with Sensei, we can already probe new parameter space. We can already sort of scratch areas that haven't been accessible just by recasting the bounds. These are the same models that I had considered sort of on the last slide. We can see again, you can dig pretty deeply into new parameter space, or the detectors that are already up and running or are planned can dig pretty deeply into new parameter space without having to do really any extra work on their end. And then I guess the last sort of fun and exciting thing that we had figured out is that once we say, okay, we have this loop, we can, through a photon, we can interact with electrons. This is essentially the same as giving this dark matter a millicharge. And there's a lot of constraints on millicharged dark matter. And so we can also look at that and use that to sort of explore this parameter space. Here are different plots about the effective millicharge. So on the rainbow bar, which is on the right side of every plot, that is what the effective millicharge that the dark matter would have if it had this cross-section and, this mass.
And what is a millicharge? Is it just, can I think of it exactly like the charge on an electron, except instead of being 1 unit of electric charge, it is much, much, much smaller?
Yeah, exactly. So it's a tiny charge. So the millicharge bar on the side, that actually is in terms of the electron charge. So sort of this yellow region here, that's 10 to the minus 8 times what the electron charge is.
So if I put it in an electric field, it would move?
Yeah, it would feel the field. Yeah, so given the millicharge, that means that these particles will see electric fields and interact with them. And we can borrow existing constraints, or some existing constraints on millicharged dark matter and apply it to these particles. So what we've got here, we've got constraints from Milky Way disk spin down, where this is that the particles are, as they move through the Milky Way, they are extracting angular momentum from it and slowing down the rotation of the whole disk. And then the other one is galaxy clusters, where there's a specific distribution of dark matter in galaxy clusters. And if that dark matter can interact with the magnetic fields in these galaxies, that distribution is going to be distorted. So both of these lines represent sort of problematic behaviors for dark matter, and it's potentially ruled out above them.
So in some ways, the astrophysical constraints are much, much stronger than our direct detection constraints. However, astrophysics constraints are notoriously messy when it comes to the actual observation.
Yeah, exactly. So there's, some uncertainty in astrophysical constraints. I mean, these are many orders of magnitude below, so there's that. But model builders are also good at finding ways to create something that maybe you don't see it in the astrophysical scenario for some reason, but it can show up in a detector or vice versa. So there is some trickery, I think, that people can do to get around it. But these are, the actual millicharges that we would predict, and these are the constraints that people who think about millicharged dark matter say are out there.
This millicharged calculation applies in the case where we're thinking about a quote-unquote light mediator, but what we call light in this context is slightly different from what we call light in the context of direct detection. Of course, in the case where the mediator is, very, effectively massless, then you can put these limits on the same plot, and that's kind of what we've done. But, when we set a quote-unquote light mediator for direct detection, what that means is that its mass is small compared to the momentum being exchanged. When we say light here for astrophysical constraints, what we mean is that it's long range enough that it's interacting with galactic scale magnetic fields. So you could have, there's certainly a range of mediator masses that you could choose that would be effectively light for the purposes of direct detection, but would still be too heavy to look like a millicharge on sort of galactic scales.
Okay, I'm again getting confused about what millicharge means, because I thought once it has a millicharge, it has the length of the electric field, so it has a 1 over r squared inverse square law.
To be more proper about this, what you get is basically an inverse square law times something that looks like a Yukawa potential, a decaying exponential. And if the range of that decaying exponential is just large compared to everything else in the problem, then it really looks like a charge. But if the range is, small compared to a galaxy, but large compared to some inverse momentum transfer or something, then you get something that sort of looks like a light mediator or a Millicharge in a detector, but doesn't quite look the same on a galactic scale.
Is this ruling out well-motivated values of these parameters or not well-motivated values? Should people be throwing these models away, or are we at a parameter range where it's still totally sensible model?
So for the direct detection scenarios, so for sort of these where we're looking at what can we do with direct detectors, at the moment I think these are models which are already difficult to use as like your ideal dark matter model, because these are cross sections which I believe are still a bit large for, I guess, some of the favorite dark matter creation stories. So for something like a freeze-in dark matter or even like a WIMP dark matter, these aren't necessarily the ideal mass and interaction parts of parameter space for those specific stories.
Just sorry, you said the cross sections are too large, meaning that the ones that you want are too large, or the ones that you're constraining are too large?
The ones that we're probing, or the ones that broadly we are even able to probe with direct detection right now.
Okay, so the freeze-in mechanism is totally healthy because it would just be way further down on this plot. Is that right?
Yeah. This is more maybe a story about what sort of parameter space we can probe right now, sort of within the technology that we have. There are probably other stories for dark matter production where these parts of parameter space would be more relevant, but maybe the popular, most straightforward stories, I wouldn't say we're carving into those.
Yeah, I can give a more optimistic answer, I guess. I don't know. One thing I would say is just if we go back to the Millicharged plot, the cross sections that we're probing, they are actually quite small. These are 10 to the minus 40 or so square centimeters, which are, not as low as you can get with direct detection experiments like xenon for nuclear recoil experiments, which go down to 10 to the minus 46 or 47, but these are getting down to quite small cross sections. In the case of freeze-in production, the target cross section usually isn't shown on plots of the dark matter proton cross-section, but for the dark matter electron cross-section in the parameter space that we're looking at, those cross-sections are sort of 10 to the minus 36 to 38 square centimeters, which if we were to put that on this plot we have of the dark matter proton cross-section, those astrophysical Millicharge limits would be a good deal stronger than that. So if you could, argue that freeze-in line is similar for the dark matter proton case than the dark matter electron case, then those astrophysical bounds on Millicharge are actually quite strong compared to the freeze-in line. The only thing that I'm not 100% sure of is whether you can map the freeze-in line onto proton parameter space in the same way. But yeah, there are lots of models that people build where you can get relatively strongly interacting dark matter, and usually it can't work via the standard freeze-in or freeze-out mechanism. Sometimes you have to have sort of unusual cosmological production mechanisms, for example, 3-2 annihilation, where you can get 3 dark matter particles come in and some process happens and that produces 2 standard model particles or vice versa, and that allows you to massively shift the abundance of dark matter that you get for a given interaction strength. So there are models people write down that live in this kind of parameter space, and because of that, just the fact that we're showing you can get down to lower cross sections than is currently possible, I think is really interesting.
Cool. You said at some point that the xenon constraints get down to about 10 to the minus 40. I guess you mean at much larger masses than what's being shown on this plot, because you have xenon on this plot, but I guess this is again the Migdal effect on this plot.
Yeah, this is the Migdal effect, but if you're talking about standard spin-independent dark matter with a mass somewhere between 10 and 100 GeV, those cross-sections are like 10 to the minus 47 or so square centimeters. Again, looking back at the Millicharge limits here, these down at an MeV are sort of not too much higher than the lowest dark matter electron cross sections that you can probe with direct detection experiments. They're the best you can do with an experiment that's even designed to look for electron recoils is sort of 10 to the minus 45-ish square centimeters. So cosmological bounds, or astrophysical bounds using this approach, are pushing down toward that level.
Okay, yeah, where to next? Both for yourselves, what are you working on next? And how should, the community of, I guess, dark matter model builders and direct detection experiment builders and astrophysicists change based on these results?
So we did sort of an easy hadronic loop calculation here, but showed that you can get fairly significant observables, even if you set up your dark matter where it's only coupled to, one particle in the standard model, it still effectively interacts with other parts of it. And so for model builders, I think this is something to bear in mind, that there might be other sneaky interactions that pop up as a result of coupling dark matter to one specific particle in the standard model. There are plenty of other versions of the calculation that we did, which might be worth doing, might be able to produce interesting results, or maybe give us access to dark matter parameter space that, for one reason or another, is difficult to look into otherwise. So, we did these loops going to a photon, talking to electrons, but one could just as easily redo this calculation, getting dark matter, which normally talks to nuclei, to interact with a different particle, or instead of a scattering, to consider an annihilation and think about what sort of annihilation constraints can one get knowing that this happens. So I think there's a lot of interesting work one could do. I think it might be very easy to get results once you can put a calculation out, because now you can borrow constraints from all different parts of parameter space and, move them over to new places.
I suppose you've got also a kind of unique two things here. Alpha U equals minus alpha D and alpha U equals alpha D. You could have other combinations in that kind of 2D space of alpha U and alpha D not being related to each other at all, I guess.
Yeah, so here we were just trying to show people how this works. And in the paper, we have the whole calculation written out explicitly. So somebody could take their own dark matter model and stick it in and then see what are the effective interactions that you get as a result. So somebody could easily take this and apply this to their own dark matter model.
And is there the possibility of getting kind of some sort of resonances or anything where for particular values of parameters and couplings, there is some very strong interaction with it, like if it relates to the actual masses of, say, a pion or something like that?
So this isn't something that we looked at, and it's something that I kind of just thought of because of your question. But Melissa, if you set, instead of having alpha up equals minus alpha down, if you set alpha up equals minus 1/2 alpha down, would that completely remove the interaction with protons, right? At least to first order. And so, yeah, you could tune those couplings such that the interaction with the pions is much, 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 much larger than the interaction with the protons. And then basically you're making a model where the dark matter doesn't interact or barely interacts with the proton, but you could still get some effective interactions through different hadronic processes.
Which might be super fun and exciting from a kind of phenomenological perspective, but from a priori well-motivated perspective, perhaps it's a little bit suspicious to set those precise values. Okay, yeah.
It was to talk to neutrons in that case. So we'd still get recoil.
Yeah, you'd still get nuclear recoils that way. People play games like this where they're trying to show why one type of detector should be considered instead of another type, and you can sort of tune the interaction with protons versus the interaction with neutrons such that, you have a model of dark matter that doesn't interact with xenon at all or barely interacts with xenon, but then other things get stronger limits. But yeah, it requires a lot of fine-tuning and is not something that you would a priori expect.
I presume that the LHC or the Large Electron Positron Collider, they're not really relevant in this conversation at all. We're not talking about interaction strength where colliding protons and antiprotons or electrons and anti-electrons, electrons and positrons should have generated a Z prime or anything like that.
I mean, I guess the bigger difference is just that those are like very high energies. So that's sort of like not so that it wouldn't happen, it's just a slightly different calculation that we'd be working with. Because at those energies, like we could actually think about quarks instead of pions and protons.
But has no one ever shot an electron and a positron in like the 80s or something at a low enough energy that would be relevant to this, like way back in the day? Or is this not something that someone could go and build? I was expecting you guys to say, no, that's not relevant. But could someone go and build an electron-positron collider at scan through the masses and try and generate a Z prime boson? Or is that not possible for some obvious reason?
No, I mean, in principle, it is something that you can look for. We definitely had people ask, could you look for signals of this kind of loop at colliders? And I am very much not a collider physicist, so I didn't want to, and I don't know about Melissa, I didn't want to try to take collider bounds and reinterpret them in a highly model-dependent way for this result. But yeah, if you assume that, you have some very light or very heavy new vector mediator that couples to quarks, there are constraints you can set on that. From the ones that I'm thinking of off the top of my head are from producing, like actually physically producing these mesons and then watching them decay, like looking for slight shifts that you would get in the pion lifetime or the kaon lifetime from this additional new mediator that would be inducing this decay. And that gives fairly strong constraints on light mediators, but not on heavy mediators. So again, it's model dependent.
I guess what I was imagining is if you got an electron and a positron and collided them, because you can fine-tune the energy of collision really, really well with an electron and a positron, right? Because you know exactly who's going to collide, whereas with colliding protons, you don't know what quark's going to collide or whatever. But and if you had somehow tuned it to the exact mass of the Z prime, presumably you would then be making the pions with exactly the right mass that somehow it would be very favored to perhaps decay into the Z prime in some way. But I'm also not a collider physicist, so I could be saying stuff that's just silly. I don't know.
I mean, naively, I think what you're suggesting sounds reasonable. Naively, I also think we might even be able to find useful information from digging through different collider experiments. We just hadn't thought about that. So that's, I'd say, even another avenue to consider going forward is how can we use this and collider data to like better explore dark matter parameter space.
What work being done in cosmology at the moment do you think is particularly interesting but perhaps unappreciated by the rest of the community?
I guess one of my favorite pet things in, hopefully this will count as cosmology, but I enjoy thinking about high energy gravitational waves. I know it's very tricky to find sources for those, it's tricky to design detectors for them, but any sort of high frequency gravitational waves are normally reserved for very exotic objects or very exotic sort of dark structures. And I think it's sort of a fun area of dark matter to think about. I think it's like a fun problem to think about. And so I'm very drawn to it from that perspective.
Yeah, I don't want to claim that this is underappreciated, but it's just the thing that I think is both really cool and also sort of the cosmology side of things, whereas most of what I do is more particle-y and dark matter direct detection, is trying to model the distribution and velocity distribution in particular of dark matter in our galaxy. Because when we do direct detection, we have this sort of fiducial model that we call the standard halo model that is essentially a Maxwell-Boltzmann distribution with a cutoff, but that sort of assumes that everything is fully virialized and in equilibrium, whereas we know that that's not totally true. We know that the Milky Way has formed due to mergers. We know that it has gravitational interactions with nearby satellite galaxies. And so, especially over the last several years since Gaia Data Release 2 came out, there's been a lot of work on this because you could take the Gaia data and use it to track the motions of stars and find kinematic substructure in the stellar population, look for stellar streams or any other sort of subpopulations that don't follow this nice simple, smooth distribution. And there's been a lot of work done using simulations to try to say, okay, how well can we look at those stellar streams and try to map them onto a dark matter population that fell in during some merger. There's been a lot of really cool work. That, as well as sort of the gravitational interaction with the Large Magellanic Cloud and how you could get dark matter sort of streaming in toward the Milky Way at high velocity from the LMC.
Thanks everyone for watching. If you like this, please do subscribe, click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both for you and the channel, because YouTube will know to recommend more stuff like this to you. And share the channel with colleagues. If you have any questions or suggestions, leave a comment. And thanks Melissa and Chris for the great talk.